Welcome to this lightning lecture. My name is Chris van Wyk, and we are going to cover binding iOS libraries. To some people, this topic may seem to be the equivalent of dabbling in dark arts, so we are going to split this up into two parts. In the first part, we'll cover the basics in terms of binding libraries for existing C or C++ code. And then we'll follow it up with Part 2, focusing on doing the same for Objective-C libraries. First, we need to cover a bit of theory. We will start by looking at the how of interrupting and linking C or C++ libraries. Then we'll look at a framework called Swig. Swig will allow us to automate the library wrapper creation process. Once we have our wrappers in place, we'll then look at creating a Xamarin.iOS binding library based on our C or C++ library. Finally, we'll use this C# library in an iOS application. Let's start by looking at a bit of theory around interrupting and linking C or C++ libraries. As part of this objective, we need to cover a bit of theory. In doing so, we'll look at some of the reasons why we would like to bind existing C or C++ libraries. We'll look at the difference between shared libraries and static libraries, and then investigate the library handling and working with interop code. As we've learned in XAM 110, Intro to Cross-Platform Mobile Development, we have various places inside our applications where we can share components or various other code that is non-specific to our application. So let's take this typical example of an application. 60% of our code can be in shared business logic, services, and even data access. 15% could be in platform-specific UI code, and 25% could be in reusable components. It is the last two items that we're going to look at for reusing components. So this can be either showing an alert, which is customized, or it could be domain-specific components that we reuse across our applications in an organization. The problem with these components is that they very much likely can be or might be Objective-C or even C or C++ libraries. And the question we now have is, how do we bring those components into our applications, which is now written in C#? How do we wrap them and use them in our apps? To answer this question, we need to look at how we create libraries. When creating libraries, we have the option to create two types of libraries. The first library type is a static library and identified by a .a extension. These libraries are also known as archives. The second library type is a shared library, and on Unix-based systems, these libraries are identified by the .so extension and on OS X by the .dynlib extension. On OS X, these libraries, when being a framework, will be an actual folder, so do look out for that. We're going to create both of these two libraries today, but eventually we'll only be able to use the static library in our iOS application. Now, to understand why, we'll need to look at these two library types in more detail. When linking is performed during the creation of an executable or an object file, this process is known as static linking or early binding. Linking is usually done by a linker, but also may be done by a compiler, and a static library, also known as an archive, is one intended to be statically linked. Now, originally, only static libraries existed before we had shared libraries introduced. And a big drawback of a static library comes in when we need to update our code. So when our code library changes, we need to relink our application to accommodate those new code changes that were made. We also need to keep in mind that all the modules required by a program are sometimes linked and copied into the executable file. In a static linked system, the generated code keeps a reference to a function, and then the linker replaces that reference with the actual address at which it loaded the function, so that the resulting binary code has the right address in place when it needs to execute that function. Now, when the code runs, it simply jumps to that relevant address and the function is available for execution. Now, this is a simple task to administer because it lets you link in only those objects that are actually referred to at some point in time. The benefit to such a static build is that it may not need any further memory relocation in the case where virtual memory is used and no address space layout randomization is required. For our purpose, we're going to make use of static libraries as this is a requirement for iOS applications. A shared library or shared object is a file that is intended to be shared by executable files and other shared libraries. Modules used by the program are loaded from individual shared objects into memory at load time or runtime, rather than being copied by a linker when it creates a single monolithic executable file for the program. Shared libraries can be statically linked, meaning that the reference to the library modules are resolved and the modules are allocated memory when the executable file is created. But often, linking of shared libraries is postponed until they are loaded. This means only a minimum amount of work is done by the linker when the executable file is created. The linker only records which library routines the program needs and the index names or numbers of these routines in the library. The majority of the work of linking is then done at the time the application is loaded or during the execution of the app. The files that we create today when we create a project or another library in our applications are typical shared libraries. So we don't need to search too far to find examples of these. We've now looked at shared and static libraries. Let's move to manage code. The common language infrastructure is designed to make it easy to interop with existing code. So let's look at an example. Let's say we want to invoke the getPID system call on all platforms that have the libc.so library installed. We could go about and write code that looks like this for our C# implementation, and then three things can happen. First, we'd be able to make the call and succeed, and then our application will execute as expected. Alternatively, we may find that libc no longer exports getPID, and in which case an entry point not found exception is thrown. Or we cannot load the library and a DLL not found exception is thrown. Now these are some of the examples of exceptions you may run into, but there's actually quite more to keep in mind when writing Invoke code or interrupting with libraries like this. As we go through the code, you may notice that some of the classes and enumerations we use resides in the system.runtime.interop services namespace, so make sure to include this into your projects. We are going to focus on the following areas. We'll look at specifying the library to import, determining the function to invoke, and then lastly we're going to spend some time on marshaling, exception management, and garbage collection. When it comes to specifying the library which we would like to use, we need to keep the following in mind. Windows makes use of a DLL extension as a naming convention for identifying libraries. On Unix operating systems, it's typically a .so or a .a depending on the library type, so either .so for shared or A for static. On OS X, it can be .so, .a or .dynlib. Now watch out for the dynlib instance. This is typically frameworks, and that library may actually be a folder of files. Now, as we saw earlier, the DLL import attribute is used to specify the library name, and it's followed by the managed code signature of the method or function we would like to invoke. Now, this all seems pretty straightforward, which it is. However, you need to watch out, specifically on Windows. If on Windows you have a library name and it contains a period, then Windows will not append a DLL to that library name specified. This highlights the fact that there is no standard way of specifying platform-specific library names, and you should watch out for this. Once we've specified the method we would like to call and the associated library, the process of execution is roughly as follows. We specify a library, and it will look like this in our code, and then we're going to have a lookup on that specific function. So our code may look like this, where we call to that hello method. At this point, we're going to assume that the function is invoked and everything happens as expected. But there's more assumptions in the background being made. The first one is the CABI being used. Now the ABI is the application binary interface, and this interface sits between two programming modules, which may often be a library or operating system. The API determines such information as how functions are called and in which binary format information should be passed from one component to the other. So it's pretty important that we have this in place. The next item is the calling convention being used to specify how we're going to call these methods and what standards will be used when passing parameters. We have two calling conventions that we can use here. The first one is the standard calling convention, which forms part of the Microsoft Win32 API. The second one is the C declaration, which is a calling convention that originates from the C programming language and is used by many C compilers for the x86 architecture. The last item here is the entry point identifier. Now, within a managed project, the original name of an ordinal entry point of a target function identifies that function across the interoperation boundary. So we can effectively rename that function that we call. Now, there's a few reasons why we may want to do this. It could be that we want to avoid using case-sensitive API function names, or we'd like to comply with existing naming standards, or we want to accommodate functions that take different data types, and then we'll declare multiple versions of the same DLL. The process of specifying methods and functions and making sure you have your calling convention specified and entry point set up can become quite tedious and error-prone. My recommendation at this point would be, if you have a large amount of C or C++ code, consider using a framework such as Swig, which will help with the automation of creating these wrapper classes. We will look at Swig a little bit later in this session to see what it will allow us to do. To understand how platform Invoke work, we need to evaluate the following statement. Given you have a managed caller, the function call, and an unmanaged callee, the function being called, each parameter in the caller is marshaled into an unmanaged equivalent. The marshal data is in turn placed on the runtime stack and the callee is invoked. Now, this sounds rather complex, and unfortunately it is. This complexity is due to how marshaling handles different types differently. For example, integers and floating point numbers are marshaled via a bitwise copy or blitting, just as it would be in the case for unmanaged code. In some cases, we can avoid marshaling, for example, when passing structures by reference to unmanaged code. However, when using strings, additional complexity is added since we need to specify the form of string conversion. For example, a UTF-16 encoded string may need to be marshaled into an ANSI or UTF-8 encoded string. Another big concept we need to keep in mind is memory allocation, since this introduces a number of additional aspects. Managed and unmanaged memory should be considered to be completely separate. Managed memory is typically memory allocated on a garbage collected heap, while unmanaged memory is anything else, for instance the ANSI memory pool allocation, or a custom memory pool, or even a garbage allocated heap outside the control of the common language infrastructure. At this point, you may argue that we could use the C# fix statement to lock a section of the managed heap, and this would allow the managed heap to be passed to unmanaged code without worrying that a future garbage collection will move the memory that the unmanaged code is operating on. However, this is completely under the control of the programmer and is not how platform Invoke works. During a platform Invoke call, the runtime does not mimic the C# fix statement. Instead, classes and structures are marshaled to native code through the following pseudo process. So as you can see, the runtime allocates a chunk of unmanaged memory, and the managed class data is copied into this unmanaged memory block. The unmanaged function is then invoked, passing it the unmanaged memory information instead of the managed memory information. And then the unmanaged memory is copied back into managed memory. Now, there's one key point to keep in mind. The memory management specified in the above process is implicit, and there's no way to control how the runtime allocates the marshaled memory, or how long it will be available. And this is really important. If the runtime marshals a string, the marshaled string will only last as long as the call. The unmanaged code cannot keep a reference to this memory and will be freed after the call ends. Failure to pay attention to this restriction can result in undefined behavior, including memory allocation violations or even process termination. This is true for any marshalling process where the runtime allocates memory for the marshal process. The one pseudo exception to this point is with delegates. The unmanaged function pointer that represents the managed delegate lasts as long as the managed delegate does. When the delegate is collected by the garbage collector, the unmanaged function pointer will also be collected. If the delegate is collected and unmanaged memory invokes the function pointer, you're treading on thin ice. Anything could happen, including a process seg fault. You must ensure that the lifetime of the unmanaged function pointer's lifetime is a proper subset of the lifetime of the managed delegate instance. So do be careful when working with delegates. Let's focus on exceptions for a minute. Platform Invoke assumes that the unmanaged code conforms to the C ABI. But C doesn't support exceptions. As such, it is assumed that runtime exceptions will not propagate through unmanaged code. It is fairly simple for an exception to propagate through unmanaged code whenever unmanaged code invokes managed code. This typically occurs through the use of callbacks, using a function pointer on the unmanaged side which can invoke a delegate on the managed side. Let's consider the code snippet here on the right hand side. If an exception were to get thrown in the handler, then that call that frees the message will not get called and we will have a memory leak. It is therefore very important that the managed code not propagate any exceptions. It must catch all exceptions, or else the unmanaged code calling the delegate will break. So do not let your exceptions propagate between managed and unmanaged code. Up to this point, we've been describing what pinvoke does. It creates C# wrappers around C or C++ code. But there's a big problem with the wrapper code we've described so far. It is possible for a race condition to exist between user code and the runtime garbage collector. The garbage collector that .NET uses is not conservative. It knows all types involved and, for instance, can distinguish between an integer that looks like a pointer and an actual pointer value. It knows all stack allocated variables and what the scope of these variables are. And finally, the garbage collector does not see into unmanaged code. The result of this is that it is possible for the garbage collector to collect a class instance while a method of the instance is still executing. But how can this be possible? If the method no longer references a class and no other code refers to it, then the garbage collector may collect the class. If no instance members are used and no one is using the instance, then in theory there should not be a problem with a collection when it happens. The problem is it does matter. It matters if unmanaged code thinks that the instance is still alive. The last item I want to talk about is disposing of resources. The garbage collector cannot see into unmanaged code or memory. It only deals with managed memory. Therefore, if you have a large amount of memory in an unmanaged memory, such as an image or video data, all the garbage collector will see is the pointer that refers to this data, and not the size of the unmanaged memory held by the managed code. As a result, the garbage collector won't know that a collection should be executed, and therefore there won't be a memory pressure that'll cause a collection to ensue. For this reason, we want to implement disposable, the interface on our objects. But we need to keep the following in mind. The .NET garbage collector does not execute an object's finalizer when the object is collected. Instead, the object is promoted a generation, and the object finalizer is executed the next time that generation is collected. The reason why this happens and why this is a problem is because the collection frequency is inversely proportional to the generation number. So generation 0 may be collected 10 times before generation 1, and generation 1 again 10 times before generation 2. So really be careful when implementing your finalizers. Up to this point, we've covered a fair amount of theory. So let's switch gears and look at practical work. We're going to look at how to implement Swig to bind our C and C++ libraries into Xamarin.iOS applications. And to do this, we're going to cover the following. We're going to look at installing Swig. Then we'll create a Swig project based on a bit of C code. And then we're going to create from that a shared library as well as a static library. And ultimately incorporate that into our C# code. The goal that we have set ourselves here is to create C# wrapper classes so that we can make use of platform invoke and reuse existing C or C++ libraries. As we've seen so far, there is a number of things we need to keep in mind when going about this. And I always look for tools which will help me automate some of these processes, especially where they can be error prone. And Swig is one of these tools. Swig is a software development tool that connects programs written in C or C++ with a variety of high-level programming languages and is ideal to create the glue code we are looking for to call into existing C or C++ libraries. For more information, and you definitely want to get more information on Swig, visit the website at www.swig.org. Our first step will be to install Swig, and we have two options of doing this. Either downloading the package from the Swig website or installing it via Homebrew. Homebrew is the missing package manager for OS X and another of these software tools that I cannot get by without. The steps that we'll follow is first to install Homebrew if you haven't done so already, and please note we do have a dependency on both curl as well as Ruby. Once Homebrew is installed, we'll in a console call brew install with the package name, and in this case it'll be Swig. Again, if you want more information about Homebrew, please visit the website at http://brew.sh. Once we have Swig installed, we're going to create our Swig project. And for our binding today, we're going to create a very basic library to bind to. We're going to return a variable, calculate a factorial, calculate a modulus, and lastly, we're going to return the current date time. As our first step, we're going to create a Swig interface file. And this interface file contains three pieces of information. The first piece is going to be the section that contains all the ANSI C function prototypes and variable declarations. Then we're going to specify the module name, and the module name defines the name of the module that will be created by Swig. So that'll be each wrapper class file created will have that name in it. And the last part here is the percentage block, which provides a location for inserting additional code such as C header files or additional C declarations, all of which will be included in the generated C wrapper code. Once we've defined the interface file, our second step is to run Swig on this interface file. And this will create three files for us. The first file will be the example.cs file that you can see on the slide, and this is our C# API. This will include the methods we will call directly from our own project. The second file is a helper file containing Swig helper methods to assist with exceptions and marshaling of types. This file also includes the platform invoke methods we will use to access our unmanaged library. And the third file is a C wrapper file, and this file correlates with the platform invoke file and acts as a glue file between our unmanaged library and the platform invoke managed code. The last piece of work that we need to do to get to a shared library is actual compilation of the C code as well as the C# code. So for now, we're going to create a shared library and test the binding on a desktop machine, and we're going to assume that the architecture here is 32-bit or i386. So we're going to add an additional C# file here with an entry point so that we can compile a console application. And then we're going to compile our C code first into object files and then combine them into a shared library. The last step here is to compile our CS code. And once we have a compilation, we're going to run that file and make sure the outcome or the result of that run is what we expect from the library created. So let's have a look at code and go into this demonstration. Let's look at the first demo for today, and this is creating our shared object library and then bindings to it, which we'll invoke from a console application. And we'll start by creating our C code here. So we'll have a example.c file, and inside it we're going to define the code that we've seen already. So that'll be a variable, my variable. Also we'll have a factorial function, a modulus function, and then getting the current time function. So I'll save this off into example.c, and then we're going to create our interface file. So the interface file, that example.i file that we've seen in the slides as well, is going to contain the definitions so that Swig knows how to create our wrapper code. So the first section here is going to define the name of our module, and this will be example. So all files created from this interface file will be some kind of example file as the name. Then we'll place the header files or function declarations, and then we'll have the prototypes for each of our functions or variables or properties that we may expose. Remember, we don't need to expose everything from our library. It's our choice how much code we want to actually make use of. So we don't need to bind everything. In this example, we'll actually bind to everything. So let me save this. And then we'll be able to run Swig on that example.i file. The first thing though is we need to specify the language we want the wrappers to be created for. So this will be C#. So we'll use the C# flag and then specify example.i. So if we look at the output of that console run, you'll notice that we now have example.cs, example binvoke.cs, and then example wrap.c. So let's look at each of these three newly created files to sort of find out what they're all about. The first file we want to look at is example.cs. I'm going to use Xamarin Studio to have a look at these files, because now that we've created them, it's going to be a little bit easier to look at the code. Right, so this file contains the API that we'll use inside our managed code library. You'll notice that we'll call into this class file, or at least into this class, and we have a property called myVariable, a method func or fact, a method myMod, and a method getTime. So this maps sort of to the example C code that, or the C code that we've written, but you'll notice that this goes off to example.platform invoke. So there's another step here that's been introduced. So let's look at this example binvoke.cs file. Now I'm at the bottom of this file, and you'll notice that this is the step that we'll be actually working with. So this will be an entry point to C# myVariable, C# myVariable get, C# fact, C# myMod, and C# getTime. So these are either the properties, but we know we only have one property, or the functions that we'll be calling into. So that makes sense. You can see that fact and modulus and getTime actually maps. So we have an DLL attribute, DLL import attribute, specifying the shared library or static library we'll be using, in this case example. But this is interesting. This is a bit different. Now the reason why we have this file is because it acts as glue in between the managed and the unmanaged world. So Swig takes care of the marshaling and all of those intricacies that we've talked about in the previous part of this class. So let's have a look at that wrapper C class file, see what's going on inside it. Right, so this wrapper file, as you can see, was created by Swig, and it contains a lot of definitions that is managed by Swig and is used to get this process of marshaling correct for us without us having to do a lot of work. What I want to do is scroll down all the way to the bottom of this file, because there's the methods that we'll be interested in for the time being. So you'll notice here, just get to the spot, roughly around here line 260, that the declarations that we've introduced into our interface file gets exposed here. And then those methods that we platform invoking into is exposed, and they wrap the original C file that we had. So for instance, to get the getter and setter correct, we have a myVariable set and a myVariable get that points to setting and getting values from myVariable. Here's the C# fact method that will allow us to call the fact function. Same for my modulus calculation as well as getting the time. Okay, so we now have C files and we have CS files. The next step is to compile all of this into workable executables. So let's start by looking at the C files first. We're going to first create object files of the C files that we have. So we'll use the GCC, the GNU Common or Compiler Collection, and we're going to use this, and we'll use as the first flag -C to say we want a compilation, and then we'll use the next flag, which will be the position independent code specification, and this is code that we'll create that is suitable for usage in a shared library. Next, we'll specify the architecture of this library, and we want this to be 32-bit, so I'll specify i386. If you don't specify this, it'll default to x64, so 64-bit code. Right, the next step is to specify the files we want to compile, and these files will be compiled into object files. So by default, you don't specify the output, it is inferred, so it'll be example.o and example.wrap.o, and if I do a directory listing, you'll see those object files. We'll now need to compile these, or at least construct a shared library including both of those object files, and again we'll use the GCC to do this. This flag specifies we want to create a shared library. We'll include the object files that we want to use, and then we'll specify the library name we want them to be included into. In this case, it'll be libexample.so. Last but not least, again, you'll need to specify the architecture, so i386, and now we'll have a libexample.sharedObject or SO file. Right, so let's take this shared library and create a console application and incorporate the wrapper CS files into it, and then make use of this shared library in our own managed world. So I'm going to create a console application, so I'll specify run me.cs as the main code file, and it will include the entry point into our application. So you can see here that main static void, and it will call into example.cs, so the API that we've created, and we'll get the variable value, we'll get the factorial calculation as well as time. So let's save this off. And then I'm going to use the MCS distributed by Mono and compile all my C# class files into an application. So we'll specify runme.exe as the output file, and we'll say please include all CS files. And once this is done, we should have a runme.exe. And now I can invoke runme.exe by calling it via Mono. Once executed, we'll see the variable myVariables value, that property returns as 3. That's what we specified in our C code. The factorial calculation of 5, which is 120, and then the current date and time. Right, so now we have a shared library, but we're still a way off to get this working in an iOS application. So our next steps will be to convert the shared library, or at least use the code to create a static library, and then incorporate that into an iOS application. So let's do that. I'm going to switch back to my slides, and we can continue from there. On iOS, static libraries are the only supported library type. This means our shared library in its current form is not usable. We will also need to recompile the library to support the iOS ARM processor architectures available. Currently, we only have a library supporting i386. To do this, we will need Xcode. I can hear a lot of you cringing at the idea, but it's a required evil at this point. I'm going to assume you have Xcode installed as well as the Xcode command line tools. However, if not, then grab Xcode from Apple's App Store. Please make sure you have the command line tools installed, since we'll need the Xcode toolchain to complete the compilation process. Once Xcode is ready, we'll follow the steps to create our static library. We'll open up Xcode, and then we're going to select the new project dialog. From here, we're going to select the framework and library template and then select the Cocoa Touch static library. The last step in our library creation is to add our example C and example wrap.c files. Note, however, we're going to rename the example wrap.c file to example wrap.mm. The mm extension indicates that we are working with a C++ compilation unit in this file, and the Objective-C compiler should treat it as such. Right, so let's switch to our demo and see how we're going to complete the rest of this compilation, because there's one or two steps that we're going to add in the build process as well. Next, we're going to open up Xcode. And once we've got Xcode open, we're going to create a new project. So we're going to select from the dialog here, we're going to select create a new Xcode project. We'll make sure that we are going to create a framework and library project underneath the iOS section. So it'll be a Cocoa Touch static library we're going to create. We'll name this library, I'll call it example. I like the example as a naming convention. And then we're going to select our current folder as the place to place this project. Right, the next step is to incorporate both of our two files. So I'm going to add to this example, and I'll select example wrap.mm and then example C, and we can add those two files. Now at this point, I'm going to remove the H file that was created as part of the template, as well as the member file that we had created for us. Then I'm going to change the target scheme for this project. I don't want to use the default build options here. I'm going to define my own. And the reason why I'm going to do this is because I want to create a fat library, and I want to use a script to create or run the lipo command, which will then create this fat library for me. So I want to include both the iOS and iOS phone versions in a unified library or static library. So to do this, I'm going to select the target here, add a new target, and then I'm going to make sure that I select a aggregate. Let's just get it from libraries. I will select an aggregate. So we'll aggregate the build, and I'm going to call this, let's call this example fatlib. Right, so that's our new target. The next step is to modify the build phase and add a run script phase. Now the script I'm going to run is going to look like this. It's going to specify the universal folder where I want to save my output. Then I'm going to run as a target the iPhone.iOS and as a target the iPhone simulator. So it's going to create a release and debug build for me. Once I've got both of those, I'm going to run lipo to create a consolidated static library, including both of those two previous created libraries. Right, so next step is to run this. Now, in order for this compilation to work, we need to go back to our original scheme here and just make sure that this compiles. So I'm going to tap on the run button, and you'll notice as soon as I do that, the build will succeed, and my library example.a file here on the left hand side has now turned to black. So it means this file has been created, and I can look at it in the Finder, and you'll see that I have a build now for iPhone OS. So this is specific to a device, and this is based on the target that's here on the right hand side. So let's change this quickly, and let's change the device to be a simulator as well. I want to build for simulator and device. So let's run this again. So now if we look at the output in Finder, you'll notice there's for iOS, or at least for the phone, as well as for the simulator. The next step is to combine those two compilations into one as a universal compilation, or at least include in a static library both versions for phone and for simulator. It'll just allow us to launch this library on both platforms. Right, so I'm going to change to the fat library schema now, and I'll run this. Now if everything executes as expected and we have a successful build, if we now look at the contents of our Finder, you'll see that we now have a universal folder as well with a single static library. So if we look at the iPhone OS library, you'll notice that this is roughly 25 kilobytes in size. The simulator file is about 13 kilobytes, and the universal file is 38. So it's a combination of those two libraries. Now we want to use this, so I'm going to copy this A file, and then I'm going to go back to our folder where we save everything, and I'm going to paste the item here. We're going to include this libexample A file in our next project, and that is creating an iOS application and then incorporating that binding, or at least that static library, with our binding. Our next step is to create the Xamarin binding project mentioned. So again, I'm going to switch to an IDE, but this time we're going to go to Xamarin Studio. So it's going to be familiar C# land to work with. So let's do that. Okay, so this IDE should look familiar. Let's create our project. And we're going to use the new template wizard in Xamarin Studio to create an iOS library project. Do be careful though. For C and C++ libraries and binding to them, we're not going to make use of an iOS binding project. However, we'll create a standard iOS library project. We'll select that template type, tap on next, and then we're going to name this library. And I'm going to name this library example lib. I'm going to drop it into the same spot that we've been saving most of our code for today. So I'll select that folder and click create. The next step is to remove the class file that we have here. So we'll remove that, and we're going to add our own CS files. So remember when we created the runme.exe, it compiled all the CS files, and for our library, we're going to add in, from that same folder, we're going to add in our example.cs file, that's our API, and the example.invoke file, the CS file. So we'll include these two files and we can copy them into our folder. The next thing we need to do is we probably want to look at our example.cs file. We implemented these methods as is into our console application, but it's probably a good idea to change these into more C#ish kind of properties and method names. So let's call this factorial, and my mod will become modulus. And then getTime, we'll create getTime. So now our API looks a little bit more decent. Once we've fixed up our API, we're going to need to spend some time on this example pinvoke file. So we have a few things to consider. In standard mono, it is possible to pass C# delegate instances to unmanaged code in lieu of function pointers. And then the runtime will typically transform those function pointers into smaller thunks that allows unmanaged code to call back into managed code. In Mono, the just-in-time compiler implements these bridges. But when using the ahead-of-time compiler as required by iOS, there are two important limitations at this point. You must flag all your callback methods with the mono pinvoke callback attribute, and you need to make sure that all your methods are static. There is no support for instance methods. Now, a way to fix this is to remove this pinvoke file, and I'll remove it from project, and then to create a script that can fix up this file for us. So let's close it here as well. Now I'll go back to my console, and I'm going to create a Ruby script that can handle this for me. So I'll call this fix.rb, and then I'm going to paste the script inside of this file. So the script is going to run through my application and then fix up the attributes as well as make all my methods static. Now, one thing I need to do here, depending on the target of your library, you will need to specify the proper namespace. Now, since this is a unified project, I'm going to remove monotouch dot and just replace this with the monopinvoke callback attribute. Right, so at this point, I can save this file, and we should be able to run it on that pinvoke file. So let's do this. I'm going to call Ruby example pinvoke, and then I want to make sure that I run the fixer, so it'll be actually ruby fix.rb, on the Invoke file, and then I'm going to create a secondary output file. So I'll call this Invoke fix. Right, so that will run. Let's pipe it to the file, and there's our file ready. Next step is to go back to the IDE and include it. So add files, I'll select that fixed file, copy it in, and then my namespace, and everything should clean up. So let's make a fix to that class name as well. It should be fine, and let's make sure everything compiles. Right, so the last step here is to resolve a namespace, and let's recheck that. Okay, so our library is now proper. The next step is to create our iOS application. So let's do this. To add our iOS application, I'm going to go to the solution, right-click, and select Add New Project. At this point, the new wizard will be presented, and I'm going to select iOS application, single view application, tap on Next, and give this project a name. So I'll call this Simple Binding. I'll create this project inside the folder that we've been using so far, and you may notice something immediately here. There's a new inclusion in our finished launching method, and that is Xamarin UI test. So we're adding in Xamarin start, and this is now part of our templates. So we now by default will have a UI test project that will accompany our application. Now for today we're not going to use it, but it's something that is quite handy to have. So for now I'll just minimize it, and let's focus on the Simple Binding project. My next step is to add in our static library. So we'll add the static library via Add Files, selecting that libexample.a file, and make sure that this now gets part of or becomes part of our application. So to do that, we're going to make sure that the properties of this file, specifically the build action, has been set to bundled resource. This will make sure that the library is available inside our application when we need to invoke it. Right. The next step is to actually include the linking for this library. Before I do that though, at some point we want to call some C# code. So we'll need to reference the example lib. So let me do that, update my references. And then I'm going to update the properties of this project. So let's select options. Then I'm going to go to build and iOS build, and then I'm going to specify additional monotouch arguments. So these arguments are going to ensure that I have the proper linking for my static library enabled. So the flags looks something like this. GCC flags, the project directory is specified, the library is specified. So this is our example library. Then we're going to force load and make sure that we load that library, that static library. We're going to make sure it is loaded. Right, let me click on OK. And then we probably want to write some code to test this library out. So to do this, I'm going to go to the view controller, and let's do the following. Just let's make sure that everything compiles. So I'm going to do a console.writeLine, and then I'm going to select from example get time. Right, so we've now added the console writeLine statement. Let's have a look and see if our application compiles. So I'm going to rebuild the solution. Just wait for the compilation to complete. Right, so that was a successful build, which means if we now change to simulator, we should be able to run this application into the simulator. So let's try that. I'm going to click run here and let the compilation complete, and then see if we can access our code. But we notice that there's an error here. We get a type initialization exception. So let's have a little bit look into this and see if we can find the problem. So we observe the detail to this exception thrown, you'll see that we cannot find the DLL. So the DLL is not found, which is quite interesting. Why would this be? So let's close this and see if we can figure this out. So let me stop this from running. So the only reason why the DLL could not be available is because it's not part of the library. But we saw that we actually checked that code in. We actually linked it in. So it must be available within the application. So let's see where our DLL invoke is looking for this. So this DLL or the pinvoke, this DLL import attribute is specifying the example library. The problem though is that our library is not a dynamic library anymore. It is a static library part of the executable. So we'll need to update example to the following. We'll need to change this to internal. So the symbols are defined within the actual executable. So let's update all the example points here, or all the attributes where example is being listed. Let's do that. Right, so let's try this again. So we still have a problem. Let's stop this and see if we can figure out. Let's show some details here. So the entry point is not found. We have an entry point not found exception, which is also interesting. It means that the function call that we're trying to call does not exist in our library. So let's close this. Let's stop this from compilation and let's do a rebuild, just to see what's going on when a rebuild is done. So it actually turns out we've got a few errors in our code here. Now, again, this is quite interesting. We saw the build complete with device. So there can be two things wrong here. If we look at the build output, we'll see that we're actually missing a few symbols. So there could be two things wrong. It could be either that our configuration is incorrect, or our library actually does not have the i386 slice, the architecture setting and code available to run on i386. So let's have a look at our console. We have two commands we can use to interrogate libraries. The first one is file. And file will allow us to do the following. It's going to tell us which slices are available within this library. And as we can see, we have ARMv7, i386 and ARM64. So it is available. The next one is to see if we can see which functions are getting mapped inside the library. So we can use nm and specify the same library file. And this will give us a breakdown for each of the architectures to show which functions are available. So there's the ARM64 bit, and then here's i386. Now the methods being complained about, if we have a quick look at the application output, the errors here, it is C# my variable get set, C# fact, and C# get time. So we can see these are being exported, so we should be able to hit them, which leads me to think that we actually have a configuration error. So let's have a look at our iOS build. Yes, we have the mtouch arguments have not been set. So let's update this to what we set it in the device compilation. And click OK. So let's rebuild now. And now our build is successful, which means if we were to run the code, we should see the datetime being printed in the view controller. Or at least not in the view controller, but the application output dialog. Right, so there's our datetime. So let's now use this on the actual view. And to do that, I'm going to open up the storyboard and add a label to my view controller. So if I scroll to my controls, I'll be able to grab a label, drop this onto the view, and then I'm going to be able to set my constraints here so that it'll always be centered. I'm going to change the label's name to time label so that I can access it from code behind. And I'm going to change the actual text here to needs to be set. So if it isn't set, we know that there's a problem by just looking at the actual text on the label. So let's update constraints, save this off, and in our view controller, let's update this line of code. So we now should be able to get hold of our time label, and we'll be able to set the text equal to get time. Right, let's test this by running it again. Right, so there's the datetime being set. So this just proves that we can bind to C and C++ libraries. It is a bit of a roundabout. We need to import or make use of Xcode to do this, and external tools as well. But the result does pay off. The amount of time we spend doing this outweighs the amount of time that we'll be investing in porting existing C code to C#. So to recap, we created our C library. We then used the headers and function declarations inside a Swig interface file. We ran Swig specifying that we want C# code to be created from that interface file, and this created additional C wrapper and C# wrappers for us. We then took the created C code with our existing library, created a static Xcode library, so static Cocos library, and we made sure that we create from the output of that compilation, compiling for both device and simulator, that we create a fat library to include all slices of architectures. So that is i386, ARM-v7, as well as ARM64. Once we have that fat library, or that universal library, we are able to create, in this example, we were able to create our API library, exposing the method calls that we're going to call into. And then we used the wrapper class or wrapper code that was created for us to do the platform invokes calls to our specific C library. So this took away a lot of the work that we would have had to do manually. Once we've created this library, the last few steps were to include the static library as part of our iOS application so that it can be bundled. And then we had to remember that we had to set for each deployment option, that is either device or simulator, that we set the build additional mtouch arguments, just to make sure that we include and force the load of that specific static library. Once this all is done, as you saw, we are able to call the functions inside our static library. And this brings us to the end of part 1. We're going to follow up with part 2, where we're going to create Objective-C binding libraries. And in those libraries, we're going to make use of another tool called Objective-Sharpie to help us create those bindings. Very much the same way as Swig to help us today. So thank you very much. I hope you enjoyed this lecture, and I hope to catch you guys in part 2. Until then, take care and bye-bye.